My name is Adam Pastor, and this is my presentation on experiment number 4, the spectroscopy of simple molecules. So to begin, the purpose of this experiment was to identify unknown compounds present in drinking water samples through spectroscopy techniques. And as a scientist, I was presented with different samples containing compounds, and I had to identify each compound and additionally present the effects each has on the body and on the environment. And in my experiment, in my presentation, I'm going to touch on the experimental, and this includes everything, including filling out the tables in the lab notebook, along with actually examining the unknowns. I'll also talk on the results section of the lab. This includes example calculations, interpretations, and graphs, along with the tables given, graphs given, and found. Then I will finally get into the final part of my presentation, which is the discussion and conclusion section. So to begin with some background, spectroscopy is the examination and measurement of spectra produced from matter that emits electromagnetic radiation. More specifically, IR spectroscopy examines light that has much lower frequency and longer wavelengths. Different functional groups are able to be identified in the compounds from this type of spectroscopy. This is an example of the table that was in the lab notebook. And for example, methanol contains an OH functional group, and T-butanol has an OH and CH single bonded carbon functional group, and we were able to tell that from the IR spectroscopy. And this is what an IR graph actually looks like. And these are the different peaks, and you're able to tell what functional groups are present because of these peaks. And continuing with background, NMR spectroscopy, the nucleus is always moving and spinning, so when the instruments turn on, it allows the molecules within a compound to be lined up, and from this the number of H's can be seen in the compound, and on the graph is the number of peaks. And the number of peaks and the ratios of all the H's allow the compound to be identified with their functional groups. And then this is the example of the NMR table from the graph. And you can tell that methanol has 2 peaks, and then the ratio there's 2 different H's with 3 to 1. And then this is what an NMR graph actually looks like. So in the experimental, there's a table in the lab notebook which listed all of the compounds. And in the notebook, the structures, functional groups, and makeup of the compounds were examined. And then from there, the IR table was filled out. And then the NMR table was filled out in a similar way. There's one column on the table which showed the number of peaks of each compound. And then the structures showed the number of H's per compound. So from there, the number of peaks were able to be told. And then the ratios were also be able to be found out. And then the different unknowns were given. And we actually received the NMR and IR graphs for both. For me, it was 16.1 and 16.2. And from there, the NMR spectrophotometer was used to find the NMR spectrum for my unknown number 16. And the same thing was done for the IR spectrum of 16. And then the ratio and the peaks for the NMR were recorded. And then for the IR graph, the peaks were examined, and these were used to identify the chemical structure of the unknowns. And then all of the data was used finally to determine what the unknowns were. So getting to my results section, this is the table I already showed you. It includes all of the different functional groups that were present in the lab notebook. And then these are the functional groups that were present in my unknown. So for number 16, OH was present along with CH and so on. And then this is the graph that I already showed you also that represents the number of, or the different NMR spectroscopy of each of the compounds in the lab notebook. And then these are the different peaks and ratios for my unknowns. So ethanol had 3 peaks with a 3 to 2 to 1 ratio of the different H's. And now this is the IR spectrum for paraxylene. Over here, it shows a clear CH group on the benzene ring present, and then also there's a CH with an H on a singly bonded carbon present. And the remaining compounds that fit the criteria of having the CH group on the benzene ring and the CH with the H on a singly bonded carbon are benzene, mesotymine, and paraxylene, and then these are the structures of each of those. And now this is the NMR spectrum of paraxylene. And up here, you see there's the peak of 1 right here, and then 1.5. So you're able to tell that the ratio is a 2 to 3 ratio. So then having 2 peaks and a 2 to 3 ratio narrowed down the only possible remaining compound to be paraxylene. And for the IR spectrum of ethyl acetate, over here there's definite CH group unassembly bonded carbon. And then there's also a CO between 1750 and 1650 centimeters to the negative first. And the possible compounds that are left are acetone, ethyl formate, ethyl acetate, and methyl acetate. And these are their structures over here. Now this is the NMR spectrum of ethyl acetate. And it will tell that there's clearly 3 peaks in a 2 to 3 to 3 ratio. So the only remaining compound possible is ethyl acetate. So unknown 16.1 is ethyl acetate. Now this is the IR spectrum of ethanol. And there's a very evident broad peak over here between 3500 and 3100. And that shows the presence of an OH group. And right here, there's a presence of a CH group unassembly bonded carbon. So the remaining compounds that fit that data are methanol, ethanol, T-butanol, and 2-propanol. So going from there, the NMR graph shows 3 clear peaks, and they're in a very evident 3 to 2 to 1 ratio. So the remaining compound that is left is ethanol. So getting into the discussion and conclusion section, the effects on the environment. Ethanol is being used in more and more in gas today. So if a car says like E85 on it or flex fuel, it's able to be have ethanol fuel used in it. And according to the EPA, ethanol actually greatly reduces the fuel economy in vehicles. So this causes more gas to be burned off. And the effect on the environment is that the air quality will decrease due to the extra gas being burned off. And ethyl acetate is listed as a volatile organic chemical, which just means that it evaporates quickly into a gas when it's given off by certain solids and liquids. So it must be disposed of properly because it can cause cancer in animals. And paraxylene doesn't have a really great effect on the environment because it evaporates very quickly because of the sun. So effects on the body of these compounds. Ethanol is actually present in alcoholic beverages, so it's okay to drink, but not in dangerous amounts. And ethyl acetate, out of all 3 of the compounds, is probably the most dangerous because it can cause a lot of irritation in the body, which includes eyes, nose, skin, and throat irritation. And it can also cause damage to the liver, kidney, and nervous system. And paraxylene can actually cause breathing and other complications in the body, along with death at high exposure, according to the public health statement for xylene. But in reality, it's really not that bad for you compared to the other 2. So the overall dangers, kind of summarizing, are that large amounts of exposure to the water samples that were collected could have very much harm to people and animals alike. And ethanol being burned in fuel has a great effect on the air quality in the atmosphere and environment. And acetate can cause cancers in animals, so it really has to be avoided. And being in the water sample is no good. So what should be done? The contaminants in the water must be eliminated before allowing humans or animals to be exposed to the water again. And more specifically, the ethanol and ethyl acetate really need to be eliminated due to their what they can cause complication-wise and irritation-wise in humans and animals alike. And these are my references. Thank you.